Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals using the concept of beta and gamma functions, right? So here again we have a very nice integral which can be easily solved by using the concept of beta function and gamma function, right? So let us start. So let us take this integral as I, and here we are going to make use of the substitution method, right? So here we'll take this quantity, that is x square is equal to t, right? So x is equal to square root of t. Let us differentiate x with respect to t. So dx over dt is the derivative of square root of t, which is 1 over 2 times square root of t. So dx can now be written as dt over 2 times square root of t, right? Okay, now see here the limits of integration vary from 0 to infinity. So when x is equal to 0, then the value of t can be obtained from this expression. So t is also equal to 0. And when x is tending to infinity, then t also tends to infinity, right? So now we can write this integral in terms of our new variable t. So we can now write I as 0 to infinity x raised to 1 by 3. Now see here x is equal to square root of t, which is t raised to half. So here we can write t raised to half raised to 1 by 3, right? And in the denominator we have 1 plus t, and for dx we can now write dt over 2 times t raised to half, right? So let us rearrange the terms. Now we can take half outside the integral. So we have half 0 to infinity t raised to, this is 1 over 6, and taking this half to the numerator we have here minus half, and then we have 1 plus t dt. So now we can write half 0 to infinity, and if we subtract 1 by 6 and half, we'll get minus 1 over 3, right? And here we have 1 plus t raised to 1, right? So now at this step, let us apply the beta function, right? Now see, the beta function is defined as beta mn is given by the integral, that is 0 to infinity x raised to m minus 1 divided by 1 plus x raised to m plus n, and here we have dx, right? So now our aim is to express this quantity like this, right? So here the variable is x and here the variable is t. Now the variable is not going to make any difference because this in definite integrals this is a dummy variable. So here we have t raised to minus 1 by 3, right? And here we have x raised to m minus 1. So if we write m minus 1 is equal to minus 1 by 3, and here we have 1 plus t raised to 1. Here we have 1 plus x raised to m plus n. So m plus n may be taken as 1, right? So now we have two equations. We can find out the values of m and n from these two equations. So we have minus 1 by 3 plus 1, solving this one. So this is simply 2 by 3. Taking m is equal to 2 by 3 in this equation, we have 2 by 3 plus n is equal to 1. So n is 1 minus 2 by 3, that is equal to 1 by 3. So now this integral I takes the form, that is half 0 to infinity t raised to minus 1 by 3. Now see, minus 1 by 3 can be written as m minus 1. So m is 2 by 3. So we can write 2 by 3 minus 1. And here we have 1 plus t raised to 1. 1 is equal to m plus n. M is 2 by 3 plus 1 by 3, right? And here we have dt. So the sole objective is to express this quantity like this, which we have done in this way, right? So now what we will do, we'll write half, and now this integral is equal to beta m comma n, right? M is 2 by 3, n is 1 by 3. So we have beta, this is 2 by 3, and here we have 1 by 3. So now to calculate the value of beta 2 by 3 comma 1 by 3, we'll make use of another important relation, that is beta mn is given by gamma m, then we have gamma of n divided by gamma of m plus n, right? So this is half gamma of 2 by 3, m is 2 by 3, n is 1 by 3, gamma is gamma 1 over 3, then we have gamma of 2 by 3 plus 1 by 3, right? So this is 2 by 3. Now 2 by 3 plus 1 by 3 is equal to 1. So we have gamma of 1. Gamma of 1 is simply 1. So I is now equal to half gamma of 2 by 3. 2 by 3 can be written as 1 minus 1 by 3. 3 ones are 3. 3 minus 1, 2. So 2 by 3 gamma of 1 by 3. And in the denominator we have 1, right? So now we have the value of I like this, right? Now here again we'll make use of another important result from beta gamma functions. So now we know that the Euler's reflection formula, that is gamma of 1 minus n, gamma of n is equal to pi divided by sine of n pi, right? So this is the well-known Euler's reflection formula in beta gamma functions. So if we compare this side with this one, then n is equal to 1 by 3. So here we have 1 by 3, here we have 1 by 3. So the value of this expression is pi divided by sine n pi. So n is our 1 by 3. So here we have pi over 3. This is n pi, right? So this is half pi. Sine pi by 3 is sine 60. Sine 60 is root 3 over 2, right? So this 2 and this 2 get cancelled. So we are left with pi over square root of 3, right? So here's the value of this integral is given by pi divided by square root of 3. And moreover, this integral can also be solved by using the method of residues, that is the Cauchy's residue theorem.